Okay, physical properties of aldehydes and ketones. All right, so a lack of a hydrogen on the oxygen prevents the formation of hydrogen bonds between aldehyde molecules. So if we have an aldehyde like propanal that's shown here, now if you remember the requirement for hydrogen bonding was to have an oxygen and a hydrogen, but they had to be bound to each other, right? So if we have something like this, we can have hydrogen bonding because the oxygen and the hydrogen are bound to each other. Now, in an aldehyde or a ketone, we have oxygens and we have hydrogens. However, you can see that the oxygen shown here in this aldehyde propanal has no hydrogen attached to it, and you see that the oxygen in this ketone, acetone, has no oxygen attached to it either. And so because of that, aldehydes and ketones cannot participate in hydrogen bonding in a pure sample, okay? So if I have two molecules of propanal, they can't hydrogen bond with one another, or if I have two molecules of acetone, they cannot hydrogen bond with one another. And so if we take a look at the molecular weights of these four compounds, so we have butane, propanal, propanone, and propanol, you can see they have very similar molecular weights. They're all around 60 atomic mass units or 60 grams per mole. But you notice that the boiling points increase as we go from butane to propanal to propanone to the alcohol. And the reason why is because the alkane, the only intermolecular forces that the alkane experiences are London dispersion forces. So I'll just put here London forces, okay? Now, the aldehyde, ketone, and alcohol, they all experience London forces. However, the strongest intermolecular forces that are experienced in a pure sample of an aldehyde or a ketone are going to be dipole-dipole forces. So I'll put dipole-dipole here. But why is the boiling point of the alcohol so much higher than all the others? It's because it can have hydrogen bonding. Okay, and you see that in the structure right here of the alcohol. We have an oxygen and a hydrogen, and they are bound to each other. And so, how do these intermolecular forces affect the water solubility of aldehydes and ketones? Well, you remember that water is a polar compound. So, water is a polar solvent and would be expected to be effective in dissolving compounds containing polar carbonyl groups, right? Remember that like dissolves like, like dissolves like. So, water is polar, and ketones and aldehydes have polar carbonyl groups. However, whether an aldehyde or ketone is soluble in water is going to have to do with the size of the aldehyde or ketone, right? Because besides exhibiting dipole-dipole intermolecular forces and attractions, the carbonyl oxygen also can form hydrogen bonds with water, but low molecular weight aldehydes and ketones are going to be water soluble. But as the molecular weight of an aldehyde or ketone increases, the water solubility will decrease. And you see that shown here, right? This is a molecule of acetone, okay, or propanone. You can see we have one, two, three carbons in the molecule. And you can see that you have the dipole in the carbonyl, right? Where the carbon is delta plus and the oxygen is delta minus because oxygen is more electronegative than carbon. And thus, hydrogen bonds can form between water and the carbonyl oxygen. You see, we have one here and one here, and that's why nail polish remover is soluble in water. But once we get to a ketone like 2-heptanone that's shown here, sure, we have hydrogen bonds between the carbonyl oxygen and the hydrogens in water, but because the carbon chain in the molecule is so big that there's going to be so many London forces that are going to dominate. So here are the London dispersion forces between these two carbon chains, and that is going to be the predominant intermolecular force, and that is why 2-heptanone is not going to be soluble in water. 2-heptanone is that actually has a fruity fragrance, and that's one of the compounds that um, gives shampoo its fruity fragrance, and it's a compound that's insoluble in water. And so when hair is washed, it's going to go down the drain.